Thanks, Lee. If you have a question about MC over I, actually, that you got to ask Lowery, because he was supposed to teach you that.
True. You ready for that?
Yeah.
All right.
He's the cameraman. What we're going to do tonight is do structural steel design, and also, depending upon the time, touch on some timber design. The problem with steel design is that we've got a new code. This is the old code, blue. How many of you out there have had steel design? Okay. How many with the blue edition? Okay. How many with a green? Well,
that's not bad.
Not bad. As it turns out, though, what we have is a new edition. It's the second edition for LRFD. You know, they want your money, so they keep publishing them. And these notes are based on the second edition. There isn't a whole lot of change between the two. I don't think there would be any problem going in to the exam with the first edition of LRFD. Now again, we're doing LRFD because that's what you asked for. I had to scramble and revise my notes. But a change between the first and second edition is that it's now in 2 volumes. So they can get double your money. And what they've done is taken the section on connections, taken it out, and put it into a separate volume, and giving you a lot more tables and design guides. Again, it's probably not necessary for the exam to have the second edition. However, if you do want it, I have coupons that will allow you to get the second volume for free if you show proof of purchase of the first volume. So if you want that, let us know and I'll send them up. Although you have to be recently graduated, I think within 3 years of college. Okay. Again, what we're going to look at is the LRFD, or load and resistance factor design. Again, these notes are updated to the second edition. The other methods, allowable stress design, that's a green volume. That's the old method. We're not teaching it anymore, the undergraduate level, and not too many schools are either. In ASD, there's a plastic design method or load factor design. No one does that anymore because that's been superseded by LRFD. Again, you can take the exam in any method that you have a code for. In LRFD, if we look at a basic design equation, what the basic design equation does is try to prevent failure. And it does it by taking the loads on the structure, and each type of load, be it dead load, live load, wind, or earthquake, what have you, it will take that particular load and factor it up. So in designing to the load magnitude that you think you're going to get, the maximum type load you think you're going to get, it's going to add, in a sense, a factor of safety by increasing it a certain degree. And the load factor is given the symbol gamma, although here it looks like a Y given the font. But now what you have to do is make sure that the summation of all your loads, the factored loads, meaning that the load, dead load and live load, will act in combination with each other. You have to make sure that the total force in your structure or member doesn't exceed the strength of the member as given by the phi r sub n, or the design strength. What we do is we calculate a nominal strength r sub n, which is usually a stress value times a section property. But what we're going to do is reduce it by this phi factor depending upon the variability that we think is associated with that member or that stress. And these fee factors are all less than 1. In this, make sure you don't forget the fee factor. But the fee factors range from 0.9 down to 0.75 for connections. Okay, and as long as the summation of your factor load effect is less than or equal to your design strength, you're not going to get failure. Okay, and that's the LRFD method. And it's different from allowable stress design, where in allowable stress, what you do is you take the stress level and divide it by some factor to reduce it down. Okay, again, what we need to do in LRFD is investigate the combination of loads, because they can act together or at the same time. But what AISC does is specify various load combinations based on research and just the expected occurrence of these loads. The first one, and there are 6 of them, but the first one is where they take dead load and factor it up 40%. And that's just to safeguard against an unexpected dead load during construction. You don't really use that all that much. The second equation deals with live load. What it will do is factor the live load up 60% and add an extra 20% to the dead load. Plus, what they'll do is bring in 50% of the expected, what turns out to be the roof live load or snow or rain, which would be primarily on your roof structure. The third equation deals with the occurrence of the live load, roof live load reaching a maximum. There again, it's 60%, and the dead is 1.2, and the live or wind is the live load is 50% and the wind is 80%. The fourth equation is where the wind goes to the maximum. It's factored up 30%. The wind, you know, can just blow so hard, and well, again, what you're actually taking is the force due to the wind, the maximum wind speed you think you'll ever get, and then it's adding another 30%, and it can just go so high. No point in over-designing. But then the live load's only 50%. And the next equation's earthquake, and the last one deals with load reversal, where due to horizontal loading, either wind or earthquake, you might have an unloading on a column where it might go into tension. So what you do is you reduce the dead load by 10%. That'd be the case where they didn't build the structure as heavy as you thought it was. Notice what happens in these load combinations is that you don't use the maximum load factor for all the loads. As an example, when the wind is at its maximum, you're only assuming 50% live load. That's done because if you're having a major storm where you get this high wind load, you're not going to have a lot of people in your structure. Okay, so that's the rationale behind that. Plus, you're not going to factor everything up to a maximum, because that'd be the case where you have your all-time wind load with your earthquake and your live load all-time maximum, and that just isn't going to happen. That's like the end of the world scenario, and we don't design that. Although I keep talking about you never get that, but everybody remember the Mount Pinatubo explosion over in the Philippines. There they had earthquakes from the volcano. They had ash, which is a roof live load, and then a typhoon came along that night, and that's kind of like the end of the world scenario. And that's why all the structures came down. Typically, though, and this is true for the exam, such that it's only 1.2 dead plus 1.6 live load. Okay, so remember to factor up your loads if you're given the service loads, or you're given dead and live loads separately. Big thing to note here is that the load factors are different from the load factors that are used for concrete or ACI. ACI, it's 1.4 and 1.7 for the live load. In volume 1 of the second edition, there's some good example problems on page 2-9. As far as the strength of the member goes, again, we're dealing with steel. You have to go back to the stress-strain curve of steel, which hopefully you remember, or I don't know if it was covered. But this is a typical stress-strain curve for steel, and two important values need to be pointed out because those are the ones that we use for design. The steel acts linearly up to a point, as defined by Fy, and that can be called first yield. Okay, and this value here may determine the maximum strength of the member, depending upon the type of member we're designing. However, even if we yield the steel, in some cases it doesn't necessarily mean that we're going to fail. The nice thing about steel, after it goes ductile, it then reaches strain hardening and becomes a little stiffer, and we can add some more load before we get ultimate failure, or the tensile strength of the steel as designated by Fu. Okay, so in design, the two strength terms that we use are Fy and Fu, and depending upon the type of member or situation that we're designing for, we'll use one or the other. Incidentally, if you went out and tried to think up of a stress-strain curve for a material, it'd be hard to beat the stress-strain curve that we get for steel, because it gives us strength and ductility, and it has linear behavior, plastic behavior, everything you'd ever want. We use various types of steels in structural design. They're given in a table on page 1-15 of the second edition. I think it's on 1-8 of, or 9 of the first edition. But the steels are given various ASTM designations, and in the table it's given it may be separated out by grade, but again you're given the yield stress or strength and the tensile stress or strength for the various types of steels. And in a problem, if you've done steel design, you know that that's a given. You have to know what type of steel you have. The mild or low strength steel that is typical of many steel members is A36. You look at A36 and you say, well, the yield is 36, and you say, well, gee, this is easy. The two numbers match, but it's just by coincidence that happens for that steel. When we get into the other steel types, you see that A572 doesn't mean that you have a yield of 572 KSI. But there we have various grades. The two steels that are typically used are the A36 and the A572 grade 50 steel. Note over here that for some of the steels, for the tensile stress or strength, a range is given. In design, typically what you use is the minimum value, unless you're told something else. The steel mill or manufacturer has to give you at least that. Very rarely will it be less than that, but that's why we use that fee factor for that case, because some days, like on a Friday afternoon, they're not going to produce a great batch of steel. And it's going to be less than 36 or 58 for the tensile strength. The high-strength steels you typically don't use that much in design. Also in that table, but not shown on this one, is the availability. It's got columns that are shaded. If you can use that steel for that particular shape or plate thickness, just be aware of that you can't use everything for everything, all steels for everything. Most of the design or problems that are given in the exam can be designed with structural steel rolled shapes. These are the shapes that are available. The most common is wide flange shape, W shape. There are your beams, columns, even tension members. Standard shape is the old shape you don't see that much anymore. It's used in applications where you have high shear. It ends up having a thicker web than the W shapes. Again, you don't use them. They're hard to get, but watch out because some of the people making up these exams are real old, and this is an old shape, and they might throw it in. Channels used primarily for tension members, angles, tension members, as well as the WTs, and they're just T sections that are cut from Ws. They're ripped right in half. The section properties for all these shapes are given in the LRFD manual, Volume 1, in Part 1. It's right in the front of the manual, just past the different grades of steel. It has all the section properties that you could ever imagine or need to use in design. Sometimes, but rarely, you end up getting a design of a built-up member where they take the flat plates and weld them together. If that's the case, you may have to go and compute section properties. So you got to fall back on strength of materials. Here, as an example for an I shape, I've given you the moment of inertia, the elastic section modulus, and also the plastic section modulus, which is something that you use in LRFD, and it's used for computing moment capacity. But it's similar to the calculation of moment of inertia. They do, in Part 4 of the manual, have section properties for selected built-up wide flange sections. If you're lucky, maybe you'll find it in there. If not, you got to go and do the actual calculation. Watch out, because in these problems, especially the structures problems, they like to throw a lot of things into one problem. Okay? What I'm going over is the design part, but in a problem, it usually starts off with some type of analysis. You're going to have to come up with reactions and then calculate or draw the bending and moment diagram. And they could add another twist to the problem by giving you a built-up member where you had to come in and compute section properties. These problems never seem to end. Okay, looking at the first type of member, tonight would be a tension member that used to be the easiest type of member to design. It's just that now at the second edition it keeps getting more complicated, but we'll kind of touch on all the things you have to look at. The limit states or the failure states that you have to design to for tension members are these three: gross section yielding, net section fracture, and a relatively new one is block shear rupture. It's not new because it's just starting to happen. It's just that we become aware of it and have been able to analyze it. But before you go and you check the design or do a design for a tension member based on these failure limit states, the first thing you want to do, or at some point you want to make sure you do a serviceability check. Okay, and a serviceability check is one where you just make sure that you're checking not against failure, but to make sure that, say, for a tension member, it doesn't have excessive vibration. If tension members get too slender, they have a tendency to vibrate quite a bit, and it can become a problem. The slenderness of a tension member is checked by taking the length of the member, L, and that's in inches, divided by the minimum radius of gyration, which is usually about the y-axis for the rolled shapes, and making sure that that ratio is less than 300. Again, watch the units, because if you mess up the units, you'll find you never have a problem, when in fact you might have a problem. Okay, looking at gross section yielding, that's rather easy. What we're trying to do is prevent the stress in the member from reaching yield. And we base it on the gross section, the actual cross-sectional area of the member. And that's not too hard to do. But remember, what we're doing is we're making sure that the stress doesn't go to Fy. because what happens is if it goes to FY, it ends up going to FY everywhere along the member, and it begins to elongate. And if it elongates excessively, it's not really going to carry a load, because the load will have to go somewhere else because of all the deformation in the member and in the structure. Okay, so that's the first limit state. What we do is, to calculate the strength based on gross section yielding, is take the cross-sectional area, the gross area, times that stress Fy, because again that defines the limit of the strength, and then we reduce it by 10%, or a phi factor of 0.9, and that gives us the design strength. Okay, so we just make sure that our factored load in the member is less than or equal to this value here. And that's all there is to it. To design, you just rearrange the equation to come up with, say, a required area. Okay, the other, or the second limit state is net section fracture, and this occurs when we have a connection or a hole in the member. The presence of the hole will cause the stress to flow around that hole, and as the stress flows around the hole, it concentrates around the circumference of the hole. And anybody know what the stress concentration is of a hole in an infinitely wide plate?
How would I know that?
Anybody care? It's actually 3 times the average stress in the plate, and that's pretty significant. But fortunately, it only occurs right in the immediate area of the hole. Okay, so it's not like the whole member is yielding. Okay, so what we'll do is not base the strength on the yield stress, Fy. We'll actually let it go up to Fu, just because it will elevate, but it still has to go, even if it goes past Fy everywhere, it's still doing it on just a small portion of the member, right at the hole. So now what we'll do is we'll base it on Fu, or the tensile stress, but now what we want to do is take out for the area of the hole, so we base it on, or the section property is the net area, where we deduct out the area of the hole from the gross section. So the strength then is given as, we'll see, we got to add another term here, but it turns out to be the effective net area times Fu times a reduction factor of 0.75. Notice that it's lower than the gross section yielding of 0.9, and that's because there's a lot more things that can go wrong in a connection than, say, along the main body of a tension member. There's more variability, so we've got to use, in a sense, a larger factor of safety here. The effective net area, A sub B, actually gets reduced some by a reduction factor U, which we'll talk about in a minute. But so A sub B is actually U times the net area of the member. Okay, the area holes. Okay, what we're doing is, again, we're taking the gross area, and it's the area of the cross section that's perpendicular to the load, or perpendicular to the longitudinal axis of the member, but we got to take out for the area of the holes. Okay, and the area of the hole that we take out is not the area based on pi r squared. Okay, but it's actually the diameter of the hole times the thickness of the plate. Okay, because that's the cross section that's perpendicular to the force or stress field. Okay, so the net area is gross area minus the area of the holes. If we got 2 holes that will involve the fracture path, and again, these members fail by net section fracture by actually fracturing or separating into 2 pieces, and that obviously limits the strength of the member there. But what we do is, again, we deduct out for the area of the holes, so the area of the hole is the diameter times the thickness of the plate. But here, we don't take the diameter of the hole. We got to make an adjustment. And what we do is, sometimes you'll be given that you've got to provide holes for, say, a bolt size. The bolt sizes are given in 1/8 inch increments. What we do is we take the diameter of the bolt the nominal diameter, and add a 1/16 inch. That 1/16 inch is for the oversize of the hole. Okay, that allows us to get the bolt into the hole. If we drill exactly a 7/8 inch hole for a 7/8 inch bolt, we may not be able to get it in there. Okay, but it also deals with the tolerance that the fabricator has in locating these holes. There can be a slight misalignment, but with that 1/16 of an inch, we can still get it in there. However, we add another 1/16 of an inch, and that is to account for the fact that we put this hole in here. Usually it's not drilled, it's actually punched. And as it punches through, or the die punches through the plate, it has a tendency to damage the circumference of the hole, and we take out that extra 1/16 of an inch to account for that. So the actual hole diameter that we use in design is the diameter of the bolt plus 2/16 or 1/8 of an inch. Okay, if you're given the actual diameter of the hole, then you add in a 1/16 inch to account for the damage to come up with the net diameter of the hole. One thing that can, yeah. Now, actually, if you're given the bolt, diameter of the bolt, you got to add 1/8 of an inch
to get the effective hole size.
to get the, well, what really is the net diameter that you use in design. If you're given the hole, you then add the 1/16 inch to get the net diameter. Okay. You'll know, though, even if they don't tell you that the diameter that you're given is for a bolt or a hole, you'll know that which it is because the bolts are given as increments of 1/8 inches. So you got 3/4, 7/8, 1 inch. The holes go like this. There'd be what? 13, and then 15 sixteenths, and then maybe a 1 1/16. Okay, the holes diameters always have a 1/16 in there to account for that. Not a big deal, but you know, you're gonna lose points if you don't get it right. Okay, they can make things complicated by staggering the holes. What will happen is in some of these connections that they'll have 2 lines of holes, or 2 what they call gauges of holes, but then they'll come in and stagger the holes. And what that will do is allow them to space or pack the hole pattern a little tighter. But what that will do is alter the fracture path. Okay, and you end up having to investigate different fracture paths. Typically we assume that the fracture path is perpendicular to the force. Okay, but that won't always be true with staggered paths. What will happen is it may fracture through one hole here. Okay, but I guess going over here, the fracture gets down to this hole and says, wait a minute, you know, I got a choice here. I can either go straight down here and fracture, or if I can cut across, pick up another hole, and then come down, I can do it at a lower load. Okay, and what it's looking for is the minimum energy necessary to form that fracture. And it's not going to do any more work than it has to, just kind of like you and me. So you got to watch out. And the way we check this is we use a correction factor. Okay, if we go and along this path, what's happening is we're picking up 2 holes, so we got to deduct out 2 holes from our gross area. But if we force the fracture along a diagonal, the surface area of the fracture path increases. So it actually takes a little more strength to do that. And we correct for that by using this factor here, this S squared over 4G, where S is the spacing between the holes that we're investigating, and G is the gauge distance, or the distance between the gauge lines or bolt lines. Okay, right here. Gauge, think of railroad tracks. The distance between rails are measured in gauge. So what we do now is, in calculating the net area, again, we start off with the gross area. We subtract out the number of holes we have in our fracture path, but then we add in this correction term to take into account the fact that we're forcing the fracture along a diagonal. I guess think of it as an extreme. If you have a hole here in your plate and a hole way over here, okay, if it comes down here and has to go all the way over here and then out, okay, it's going to take a large force to do that because of this long fracture path. Well, that gets corrected by this factor here. But what you do is the correction factor is put in for each diagonal path that you have on the fracture path that you're investigating. And don't forget to multiply this by the thickness, because it's actually an area term. A common mistake is to forget the thickness. Okay, but again, it's also plus, and it helps you. So what you have to do, if you have a staggered pattern, is go and investigate the different possible fracture paths. And here as an example, say we have this plate that's a 1/2 inch by 8 inches, and it's got this staggered pattern where the spacing actually changes, kind of goes 2 inches, 5 inches, and then 2 inches, and here the gauge is 4 inches. But now one possible failure would be through what's designated as 1, comes down to this hole, cuts across, and then down here. Okay, another possible path would be 2, comes down here, comes across here and down. By inspection, usually you can eliminate a fracture path. You can eliminate 2 because this diagonal path is longer than this one, so you know this is going to take a higher force to fail than that one. Okay, but they both involve 2 holes. Another possible one would be 3, where it just goes straight down through 1 hole. Okay, so now the question is, which one's worse, this one or this one? Okay, 1, we're taking out 2 holes, but we got to add in some area due to the slant or diagonal path, and here it's only 1, but it's straight across. So we go and we do the calculation for each path. The first one is what this one here. It's the gross area, which is this, minus the area of the holes. There are 2 holes. The thickness of the plate is a 1/2 inch. The net diameter is 7/8 for the bolt diameter, plus the 2/16 for the oversized, plus the damage, plus the S over 4G. There's only 1 diagonal path on that fracture path, so we only do it once, but it's 2 for the spacing and 4 for the gauge, times the 1/2 for the thickness of the plate. Again, don't forget that, and it comes out to be 3.13 inches squared. 2, we said by inspection, we already know it's not going to control, but running the numbers, you see that it comes up higher. And again, the smallest net area will control the design. 3, that's going through 1 hole, so it's the gross area, which is 4 inches squared, minus 1 hole, which is 1 hole times the thickness times the net diameter, which is 7/8 plus 1/8. And that's 3.5 inches squared. So this is the smallest, so that would control the design of the member. So now I don't think I do it, but the design strength based on net section fracture then would be 0.75 for the phi. We'd use FU for the stress. It's not given, but it'd be, if it were A36 steel, it would be 58 KSI. And then the net area, which is 3.13, and whatever you get, that would be the strength based on net section fracture. And you'd have to check gross section yielding also, and the smaller of the two would control. Okay, another problem, though, that we have with tension members, and it deals with stress concentrations like we had with holes, is that we don't always connect all the elements of the cross-section at our connection. And what happens is we end up with an additional stress concentration. Here, as an example, we're looking at an angle. And the angle is comprised of two legs. What we're doing is we're only bolting one of the legs down to a gusset plate or some type of a flat plate. Can be bolted in. Now, somewhere down along the length of the member, the stress is uniform. But as it comes up to the connection, what happens is all the stress that's in this upper leg that's not connected has to flow down into the connection. And as it flows down, it concentrates in that leg and can overstress the connection or that lower leg if we don't adjust for it. Okay, and we adjust for it by using what we'll see in a minute, but this U factor. Okay, what's actually happening is as the stress flows down into the connection, and again that's where the stress or force is going out, it leaves the upper angle, and the upper angle may not be carrying any load, or a portion of the angle will not be carrying any load. So we end up with a portion of the upper leg that's ineffective in carrying load, so we got to, in a sense, reduce it. So what we do is we take the net area where we're adjusting already for the holes and reducing it by a U factor. Okay. This problem gets worse as the total length of the connection gets shorter. Okay, because what happens is the stress has to concentrate sooner to get out of the connection. If the length is relatively long, there's a smoother flow of stress through the connection, and the problem is not as severe. Okay, so the ball game, or the name of the game here is coming up with U. Okay, U is a reduction coefficient, and again it's used when the load is transmitted by bolts or welds. We have the same problem with welds, but they're transmitted through some, but not all, of the cross-sectional elements, meaning that there's some piece of the element that's not connected. And again, what we'll do is we'll take the net area and reduce it further by U to get it down to an effective net area. Okay. Now, new to the second edition, although I think in the first edition it was back in an appendix, U can be calculated by the following: 1 minus x bar over L, where x bar is the connection eccentricity, and all that is, going back a page, it's the distance from the plane of the connection to the center of gravity of the cross section. Okay, because the force in the member away from the connection is actually at this point here, and so think of that force having to come back down to here to get out of the connection. And then L is just the length of the connection, the total length of the connection, or it'd be the spacing of the bolts from the first bolt to the last bolt. Okay, you can use this. However, if you grew up with the first edition, there are tabulated values for U, or a simplified procedure for getting U. And they're outlined in this table here, and it depends on what type of shape we have, and in some cases it's depth and how many holes we have in the connection, because that relates to the length of the connection. But U is equal to 9 if we have a W or a WT, and the width of the WWT is at least 2/3 the depth. Okay, what happens is if we don't exceed this, then the member ends up, the element that we don't connect ends up being a significant portion of the cross section, and more stress has to flow down. So 0.85 here is for W's and WT's where the width is less than 2/3 of depth. Also for C or channels and L or angle shapes with at least 3 bolts in a line. And if we don't meet either of these two, then all other shapes with 2 bolts in line, U is 0.75. You never use just 1 bolt in a connection. You can't, it doesn't go, just kind of, you bolt here, it'll just rotate around and hit someone in the head. And, plus it ends up overstressing the connection anyways, which we'll see later. Also, remember up here for 0.9, you also need at least 3 bolts. Same thing happens for welds, although we only use the 0.9 or 0.85 depending upon whether we have a WT or W shape with the flange greater than the 2/3 the depth, and all other cases you have that. If it's welded and you're in doubt, just be conservative and use that, and don't worry about this anyways. We'll talk more about this at various times, but in this exam you like to be conservative because they can't really grade you wrong for being conservative. It may be expensive, but it isn't wrong. Okay, looking at an example, say we have this L 6x4 by 1/2 inch thick. Again, here what we're saying is that this is 6 inches, this is 4 inches, and it has a thickness of 1/2 inch. We want to know what the reduction coefficient is, what is U, and also what the tensile capacity or design capacity is of the connection. What we'll do first is, go get your section properties. We're going to need the gross area, which is 4 3/4 inches squared, plus the X bar, which is also given in the tables, section property tables, part 1, and it's almost 1 inch. Okay, you can come in and calculate your U from that equation. So it's X bar, 1 minus X bar over the length, which is 6 inches because it's from the center of the first bolt to the last bolt. That calculates out to be 0.84. If you went and used the simplified procedure, it's an angle. Just going back, it's an angle. We can't use 0.9 because it's not a W or WT. It's an angle and it has at least 3 bolts in line, so 0.85. So it gives pretty good correlation between the two methods, and this would certainly be easier as long as you can read that table. Net section fracture then, again we do the net area and then reduce it by our U of 0.85. The net area is the gross area minus the holes that we have in the fracture path. Again, what happens is it's going to fracture through perpendicular to the force, so it only goes through 1 hole. Don't think because you have 3 holes that you got to take 3 holes out of the fracture path. Again, looking down on the member, like so, we have this, and the force is up here, so what's going to happen is it's going to fracture straight across like that. Okay, so it's just 1 hole, area of the hole, and again, we got to add that 1/8 inch. That's the thickness. Like this all gives us the net area times U times FU for A36 steel times the reduction factor of 0.75. It comes out to be 155 kips. The gross section yielding, again, is based on FY. That's 36 KSI. The gross area times the reduction of 0.9, that's 154. So this controls, but not by much, and actually is a pretty good design because it's balanced. Okay, you're not losing any strength in the connection. These are just another examples of U's, or what we're really dealing with here for a U of 0.85. Again, we need 3 bolts. If it's bolted, again, 3 bolts in line or along the gauge line. Remember again that the fracture path is going to occur perpendicular to the line of action of the force. Same thing with the angle. The same thing can happen when it's welded. Okay, we just weld, say with a fillet weld along here. That again, we're welding just here and here. We're not welding or connecting in the flanges of the channel, and the stress will concentrate out here. Same thing with the angle. If we bolt a flat plate to a flat plate, we're not going to have any reduction factor because we've connected all the elements. In a flat plate, a single flat plate, there's only one element, and that's got bolts in it. Okay, so U is always 1 for that case. However, when we weld, we may have to have a U less than 1, and the problem occurs when we use fillet welds, but we only use fillet welds along the longitudinal direction or axis of the member where we don't have any end weld. If we do this, what happens is the stress as it comes into the connection can't flow straight down to the end. It's got to come out the side welds, so it does this, and as it does so, it concentrates right here. You get that same stress concentration. That stress concentration is a function of the length of the weld and the width of the plate, W. Okay, and then this criteria here tells you what the U is. As long as the length of the weld is at least 2 times the width, there's no problem. But you get below that, you have to start reducing or using a U less than 1. And this really gives you a limit on the size of the weld or width of the plate. That weld length has to be at least the width of the plate. Get below that, you got really a U that's too low that you really shouldn't be using for design. Okay, the third failure state that we got to worry about with tension members is block shear, and that's where the fracture path in net section fracture finds another shortcut. Okay, and it says, wait a minute, instead of going where I think you think I'm going to go, I'm going to take a shortcut because it'll take less load or less energy to do that. And a case in point would be an angle that's connected in with 3 bolts. It's going along here, and you thought maybe the fracture path would come straight across. Again, we said it's perpendicular. Okay, but what it does is say, wait a minute, if I take a turn here and cut around down here, I can do it at a much lower load or a lower load than what it takes me to do this. And again, it's going to go this way if it takes a lower load. And the same thing happens with a channel. You get this. It's going to happen when you bolt in the flanges of a W shape or a WT. The thing to realize is that for block shear, what has to happen is you have to surround the whole block pattern. You have to involve the whole block pattern for block shear. What can't happen is to have a fracture path that comes down through here and then out, because that won't allow the member to separate from whatever is connecting to it. Or, you can't fracture through this hole and then come out here and have this little piece all of a sudden just go ping and fly off the end of the member. Okay, so you got to go like this. That way the whole member can tear out from the connection. Okay, how do we handle that? Well, we got 2 equations that we use, and it really involves a mixed mode of failure. We'll get, because the fracture path goes perpendicular and then it cuts across parallel, the fracture path will involve both shear and tension. And what you do is you define your fracture path, and again, it has to involve all the bolts. And then you start looking at, well, this one involves tension, and this one involves shear. If the fracture path is perpendicular to the force, that's tension. If it's parallel, that's shear. But through experimentation, what they found is that the failure will involve fracture on one plane and yielding on the other, or it will reverse. And so you end up designing for two equations. One that, say, has tension fracture and shear yielding, and the other one is tension yielding and shear fracture. That just kind of flips. And so what you have to do is calculate, in this case, when it's tension fracture, when you see fracture, you always base things on the net area, and shear yielding, you always base the area on the gross section. But now you got to do the area that involves that actual fracture block. Okay, so here, the net area here would be, as it turns out, the distance from the center of the hole to the edge of the plate times the thickness, and then take out for the area of the hole. In this case, though, because the fracture path is coming into the center and going out at 90 degrees, we only subtract off half a hole. And we'll see this in an example. And over here in the shear area, it's yielding, so it's the gross area, so it's this hole length times the thickness. We don't take out for the area of the holes when we're looking at yielding. Here it reverses the shear. It's in fracture, so we need a net area for the fracture. In tension, it's yielding, so we use a gross area. When we have a shear failure, to use Fy or Fu, what we have to do is reduce it by 40% or use 0.6 Fu or 0.6 Fy to adjust for the fact that it's a shear failure mode, not a tension failure mode, because when we get these through testing, we're doing a tension test, not a shear test. And as it turns out, things will fail in shear at about a 40% reduction in load or stress. But what you do is you go and you have these two equations, but you only use one of them, and the one you use is the one with the larger fracture term. And don't ask why that is. It's kind of hard to explain, but just take it on faith. And again, we'll see it in the example. Say we've got this member here. Say it's a 4 by 4 by half, meaning each leg is 4 inches and the thickness is a ½ inch, and we have this failure or block shear failure. Want to investigate it. First thing you want to do is to find your block failure, be like that. Calculate the gross areas. There's going to be a gross area in tension and one in shear. Actually, I think the subscripts are reversed. It should be, it really doesn't change things. But now in tension, the gross area in tension is going to be this area here, which would be the distance, which is 1½ times the thickness, or 3/4 inches squared. The gross area in shear is from the center of this hole to the edge of the plate, so it's 7½ inches times the thickness of the plate for 3 3/4 inches. Then the net areas, or the gross areas of the tube minus the area of the holes. For tension, we only have half a hole diameter in that tension plane. So here the bolt holes, these are just holes for bolts. They're 13/16, and again we know it's a hole because of the 16 here. So we add in another 16 times this, I guess, is the thickness, times a half a hole, and that gives us a value for the net area in tension. For shear, again, you take the gross area in shear, subtract out the number of holes. Again, it's 13/16 plus the 16 times the thickness of the angle times the number of holes, and it's 1, 2.5 or 2.5 holes. So these give you your 4 area terms that we can use to plug into the 2 equations. So the next step is to look at the fracture terms in the 2 equations. There's one in each of them, and again, you know which term is the fracture term because it has Fu. Okay, that's fracture. and you evaluate that term, or the two terms, and FU goes with the net area and tension, and 0.6 FU goes with the net area and shear. And you calculate those two, and you use the larger of the two. Or use that, or you actually use the equation that contains that term. Okay, so you go and you find that term here, which is right here. So you use that equation. You got that value already. You got to calculate in the gross yielding on the tension plane, which is the gross area times Fy. You sum the two, reduce it by the phi factor 0.75, and it comes up to about 90 kips. You also want to take or check net section fracture. Again, calculate a U. In this case, it goes down to 0.80, and you say, wait a minute, if you go back to the previous page, you only got, what, 3 bolts in line for an angle. You can use U equal 0.85, and I got a little strength out of there if you want. Using 0.8 though, plugging it in, you find based on net section fracture it's 115. Gross section yielding, the gross area times Fy times 0.9 for phi comes out to be 122. You evaluate the three values from each limit state, and you use the smallest. Okay, because what's going to happen is it's going to fail in block shear rupture at that lower load before it can reach either of the two other higher loads. Okay, any questions on that? Need a break. Don't go anywhere. Okay, that's it for tension members. Again, a good problem that if I were making up the exam, I'd probably give something like we just went over, because what it does is it involves the 3 limit or failure states, and kind of gets everything in there. What you could see possibly is a problem that's similar, but has 2 lines of holes, but now they're staggered. And that would change things because the net area would change, and you'd have to go and you'd have to investigate the diagonal fracture path, whether it goes through 2 holes on a diagonal or it goes straight across. Okay, but I think if you go in the books that we sent up, you'd find a problem similar to that.
I've got some good examples, yeah.
Next topic, columns. Okay, the AISC LRFD design provisions for columns are based on Euler buckling behavior, and I believe you just touched on it in an earlier session. The reason why they do that is because it's very easy to describe the buckling strength or load of an Euler column. So what the design provisions do is kind of relate everything back to an Euler column. And what's unique about an Euler column is the fact that it has pinned ends. Okay, as it turns out, in reality, we don't have too many columns that actually have pinned ends. A pin and a roller. You can't go down to the store and buy these too easily. So the problem in design is, because the design provisions are based on Euler behavior, you got to take your column and kind of relate it back to an Euler column. And you do that with this value K, the effective length factor. And by adjusting your actual column length, what you can do is get it back to an Euler column, and once you get it to an Euler column, you can then use the design provisions. So a major component of a problem dealing with steel columns is figuring out what K is. Okay, if you don't know what, or you can't calculate K, you really can't do any of the other design correctly. And we have 2 sets of Ks, depending upon whether or not we brace the frame. Okay, bracing, which can be in the form of just, it could be wires or rods or angles, or it could be a concrete block wall. But what bracing does, in a sense, is it prevents the joints from translating when the columns buckle in the frame. And that becomes very important, because we'll find that if the frame is braced, the column strength is much higher than if the frame was unbraced, or, as we'll see in the next drawing, the joint can sway as the column buckles. Okay, but the AISC design provisions give you 6 simple cases for end conditions of a column, and the first 3 of them relate to a brace frame. Okay, the first one is where it's pinned at both ends. That's Euler. So we're already at Euler, so our K, which relates us back to Euler for our length, is going to be 1. Okay, but another case would be, what if we have fixed ends of our column? Okay, what that's going to do is force the column to buckle into a tighter mode. Okay, it can't rotate at the ends. And what it will do is cause, or ends up increasing the buckling strength, because it takes a higher load to force it into this tighter shape. So what happens is we end up with a K for design that's 0.65. So what we'll do is take this K of 0.65 and multiply our length by 0.65, and in fact we'll go into the design with a shorter column than what we actually have. And that should make sense if, by going back, and I don't have this drawn, but if you go and you plot Euler buckling load versus, say, the column length, you get something that looks like this, meaning that the longer the column, the lower the buckling load. The shorter the column, the higher the buckling load. Okay, so by coming in with a reduced length, we're going to come up with a higher load if we go and we use the equations based on Euler. Okay, another case would where we kind of mix and match end conditions, but here we've got a fixed and a pinned that's somewhere in between the two. We end up using a K of 0.8. Okay, note that if the frame is braced, usually in a problem it's going to tell you whether the frame is braced or not, or you'll see diagonal bracing or something. But if it's braced, the K is going to be less than or equal to 1. The other case is the unbraced frame. That gives you the other 3 idealized cases. What happens in an unbraced frame is, as the load increases, the column says, wait a minute, it's getting hard to carry this load. If I just kind of sway out to the side here, I'll buckle and get rid of this load. And it will do that because it can do it at a lower load than if it stays, if it doesn't translate up here and let the load increase. Okay, and that's idealized by these 3 cases here. The first one is if it's fixed, and then up here we have the translation, but it can't rotate. So it goes out like this, like so. And that would be the case where you'd have a very rigid cross beam up here, where it would go off like that. Over here, the K for this first case is 1.2. This is what we call the flagpole case. They like designing a flagpole. The top can rotate and translate. That's 2.1. That's kind of the worst case we have. The last case is where it's fixed but can translate up here, but it can rotate at the bottom, so it's a little different from what we had here. That's 2. Again, for these idealized cases, that K is greater than 1. Okay, meaning now when we go in, do our column design, we're going to take our actual length, multiply it by K, and we're going to go into the design with some larger L. Okay, so it's like now we got a longer column than we thought we had. So what's going to happen is that the critical load or design load is going to go down because of that. Okay, we looked at these idealized cases. Unfortunately, we don't always have those idealized cases or end conditions where it's pinned, fixed, or we got this block that can translate but not rotate. In that case, what we have to do is come up with some method of determining the stiffness at the ends of the column. Okay, the stiffness due to the other members framing in will give us a condition that's somewhere in between being pinned and fixed. Okay, but what we do, though, is we evaluate the stiffness of each end of the column using the G term, or it's called the relative stiffness. And we calculate the relative stiffness by looking at the summation of the column's stiffnesses, or vertical members that come into the joint, divide that by the summation of the stiffnesses of the bending or the beam members or horizontal members that come into the joint. Okay, so this ratio here is the moment of inertia divided by the length of that member, or the column here, and here it's G, or for beams or girders. Same thing, the moment of inertia of the beam divided by its length. You sum that up for all the columns that come in. Here there would be two columns, top, above and below the joint, and the beams or girders, we have two beams coming in. You do that calculation, you come up with a G, you'll get a G for the top, a G for the bottom. Once you get that, you go to what we call alignment charts. These are in the specifications. I think I give you a page number in the notes. I don't have it here. But what you do is, say for the top, you had a G of, making up numbers, say 2. And at the bottom, GB, say it came up as 0.5. What you do is you get those 2 points and take a straight edge, a credit card or a license or whatever you have, draw a line to connect to the two, and then wherever it intersects this center scale is your K. Okay, so in this case it's 0.756, maybe 7776. Now note that there are two actual sets of alignment charts. One is for side sway inhibited. That really means, I don't know, braced. You can't have side sway. And if it's uninhibited, it's unbraced. Okay, I tell my students, scratch this out and write this in. It's just confusing, the terminology that they use. But you should be able to tell, because note that for the alignment chart on the left, the K ranges from 0.5 to 1. And we said if K was equal to or less than 1, was the frame braced or unbraced? Right. And note here.
So at the bottom of the chart.
Yeah, it's if it note over here, it ranges from 1 up to a practical limit of 20. It's greater than 1, so K is greater than 1, so it's unbraced. Don't get confused, because if you mix it up, it'll be wrong. Don't worry what's the top or bottom. Note that for GA and GB, the scales are the same. You could have gone in here with 2 here and 0.5 on this side, and you notice that they intersect at the same point. Okay, the problem with columns is that they don't have the same stiffness about... Oh, question? In a frame, you can have braced and unbraced members, although they would occur on different stories. As long as If you're given a problem where you have a building frame like so, say it's 1 story, and they only have diagonal bracing in 1 bay, or down here. Okay, you say, well, gee, these 2 columns are braced, these are unbraced. But realize by putting the bracing in 1 story, you prevent these joints from translating, but because they're all tied in, you actually prevent this one and this one and this one, meaning that really the whole frame is braced.
Now, how about the mixture? Did you say, is there...
Well, if you had another story up here, like so, that had no bracing, then these up here would be unbraced and these would be braced.
So they'd be designed with on different sides of those tables?
Yeah.
But you don't expect something like that on quiz, do you?
No. I mean, it's an unpractical situation. Typically, you'll see bracing go up the same bay all the way up the building. Okay. If the building gets really long, they need maybe two sets, but you don't have to do this everywhere. What's the problem with that?
No doors.
Yeah, where's your windows and doors going to go? Okay, with columns, the problem is that their stiffnesses differ between the 2 principal axes, XX and YY. All things being equal, what's going to happen is this column will buckle out about the weak axis, okay, because it gives the least stiffness of the 2. What makes things complicated, though, is that our end conditions can differ for the 2 axes or directions. So what we have to do is evaluate the not just the length or the radius or duration, which is a measure of stiffness of the column, but we look at KL over R for both axes. Okay, so again, what can happen is you can actually have all 3 of these terms differ for both the X and Y. And what we'll do is use the larger of the 2 values to control the design. Because as the column slenderness, which is measured by KL over R, increases, the buckling load, or P critical, goes down. Okay, because as this value goes up, it means the column's getting longer and more slender. It's going to behave like a wet noodle, I guess, or maybe an uncooked noodle, it's a piece of spaghetti. Okay, so use larger. When you do this calculation, make sure that L, or the length of the column, is in inches. Otherwise, you get a small value. If you keep it in feet, it looks like you don't have a problem. The number is way off. But now in LRFD, what we don't do is use this for design. We take it and we modify it to come up with what we call lambda sub C. It's a column slenderness parameter. It's KL over R. We divide by pi and then multiply that term by the square root of Fy over E. Okay, and this just gives us a value that is easier to put into design equations than this. As you'll see in a minute, what we do is we take that lambda sub C and see where it falls in relation to 1.5. Okay, because 1.5 is a dividing line between 2 design equations. We only got two real equations in column design. If lambda sub C is less than or equal to 1.5, then we use this equation to calculate a critical buckling stress, which in theory, this is the stress that the column's going to buckle at. So that defines the limit, or the strength of the column. If lambda sub C is greater than 1.5, then F critical is given by this value here. And again, note that they both have lambda sub C in there. Actually, it's lambda sub C squared. You can also use tables to do this design to come up with F critical, which again, in an exam like this, you want to try to use the tables as much as possible to save computational errors and time. although it assumes that you can read tables correctly. The design load then is that F critical that we got from up here from either of the two equations times the gross area times a reduction factor phi of 0.85. Okay, here we use the gross area. We don't have to worry about holes in the member because the member's in compression and it's not going to fracture like a tension member. Okay, so now just for information, if you plot the column slenderness, lambda sub c, versus the ratio of F critical to Fy, the maximum you could ever get for F critical would be Fy, be for a real short, stubby column, and that would occur when lambda sub c goes to 0. But as lambda sub c increases, then F critical begins to decrease as defined by this equation or curve. Here is 1.5, and then we pick up the second equation. Not that you need this for the exam, but it just shows you where everything's coming from. With columns, not only can they buckle globally or about one of the other axis, X or Y axis, you also have to check local buckling. Okay, local buckling is a phenomenon that will occur if the individual elements of the cross section get too slender, meaning that their length to thickness ratio gets relatively large. And we need, typically, you kind of have to do a quick check for that. You check both the local buckling of the flanges and the web. The flange element that we look at is actually half the flange, so it's the flange width divided by 2 times TF. I don't know if there was an error in the notes. This may have been T sub W. We calculate that slenderness and compare it to the limit here. Make sure it's less than that. We do the same thing for the web, H over the thickness. These values are also given in the section tables. You don't have to calculate them directly, or you can pull them out directly, the ratio, and check the web against local buckling against this ratio. Okay, local buckling, what happens is the individual element just kind of buckles, crimples all along the length of the member. And once that happens, it can't carry any load in that portion of the element, and the whole column quickly goes to failure.
Okay, you're saying this may be wrong in their notes?
This subscript may be wrong. Is it, say, this is correct, should be TF. Is it TW in the notes? Now, just corrected, but you'd go into the section tables and find this whole term anyway, so you're not going to make an error on that. All these equations have actually been calculated, or the design strengths have been calculated for you for the various columns that are used. Typically, we use W14s, W12s, and maybe a W10 by sections. These column design tables, they're in part 3. What they do is they give you the design capacity for the columns based on 2 grades of steel, 36 KSI and a yield of 50 KSI for various effective lengths. KLs, that's kind of cut off here, but it's KL, but it's for KLY. Okay, it's for the weak axis buckling of the column. The reason for doing or giving you just the Y is, I guess, to save paper or space. If they gave you also KLX, now these tables would be double. Okay, but you can actually quickly come up with the buckling capacity in the KLY, in the KLX by taking the KLX and dividing by, I don't know if you can see that, by the ratio Rx to Ry. And that will reduce it down to an equivalent KL in the y-axis. I think I have that on the next sheet here, like so. So again, the tables are given for the weak axis. We can evaluate our column for the strong axis by taking the KL over R in the x-axis dividing by the ratio Rx to Ry. This value here is given at the bottom of the tables there. If you go into the manual, I think on what I sent up there, I cut off the bottom, or the bottom's actually on that view. Okay, the whole problem though, if you have to design a column or select a column to resist the load, you don't know what this value is. And the next example problem just kind of shows the procedure for doing a design. Okay, here say we've got a column that is subject to an axial load of 750 kips. We want to design for the lightest W12 bisection. We're going to use A36 steel. First thing that you do is come up with your effective lengths for the two axes, but note that they're not equal because the end conditions differ. Okay, here we got that block that translates but doesn't rotate, and a pinned end. That means that for this axis, the K is equal to 2. Y, when it is fixed and pinned at the bottom, K is equal to 0.8. So now, calculating the effective lengths in the x-axis, it's 40 feet, and the y, it's 16. Okay, and you say, well, gee, 40 feet is quite a bit longer than 16, so 40 has to control, but you don't know that because you still don't know what the radius of duration is, or you really need to evaluate KL over Rx and KL over Ry to see which one controls. You'd use the larger of the two, but the problem is you don't know what this is, the radius of duration, because you haven't selected the column yet. Okay, to approach the design, what you do is you go and you calculate the ratio of the effective lengths, which turns out to be 2.5. Okay, now if you could pick a section that had a ratio Rx to Ry that was equal to 2.5, what that would tell you is the column would buckle in either axis at the same load, and that'd be a very efficient design. The problem with all that is it's very hard to select a column based on this ratio, because if you look at these ratios, they just don't vary that much. In fact, for the W12s, they range from 1.75 to 1.8 for the W12 with capacities near 750 kips. Okay, so what do? Well, since this ratio is 2.5 and the actual ratios of the radius of duration Rx to Ry is 1.75 to 1.8, that's going to tell me that I'm not going to have enough Rx to match this 2.5, which is going to tell me that the x-axis is going to control the design. Okay, that's kind of bad news, because now I don't have column tables to use, because everything's based on the YY buckling. Okay, but if I look at these values, I say, gee, they don't range too much, so I can estimate my ratio Rx to Ry as 1.75. So what I will do is come up with my equivalent KL in the Y direction for my x-axis by taking the effective length in the x-axis divided by that ratio, and now it's 22.9. Okay, so now what I can do is go in with 23 feet into the tables and select a section. Okay, the problem is the tables aren't divided up. I think it goes 22 feet and 24 feet. So I find for W12 by 136 that the design load is 788, which is greater than 750, which is what I need at 24 feet. I got 23 feet, so that'll work. I think if you go into those tables and you look at the next lighter section, it doesn't give you enough strength. Okay, so again, you know, to really understand this, you'll have to go back and study it, but what you want to do is get to know how to use those design tables, because they'll save you a lot of time. I don't think you really have a prayer of doing the problem without the design tables.
So what you're saying really then is you just come in here at 23 feet on the left-hand side of the chart, and you go across all these sections till you find somebody who comes up with this much section.
Yeah.
Okay.
Let me, if I can do it real quick.
Yeah, the only.
Let me.
Yeah. Okay.
Let me.
You're the only one's got a book here.
I did bring my book. If he'll.
All right.
I don't know if you can see this.
Yeah, you can do that. You may have to put it kind of where you want us.
Can you see that? Hello?
Okay. Okay, go ahead.
Well, I gotta get to the right W12s.
Right. You have to hold it still for a while
Yeah.
until it settles down.
Okay, see that?
Is that the right one?
I gotta move it.
Go ahead. You're going to go to 23
Okay.
feet?
Well,
There's 23 feet.
note that 23 feet isn't here. Okay, so it's conservative to go up to the next foot. Okay, because it makes it a little longer. Okay, but you come across, and let's see where I'm at.
Well, I see what you're doing anyway. So in other words, you're going to come on across the section here.
Yeah, okay. See, at this one, you don't see the full table. This is a W12 by 210. At 24 feet, I'm at 1260. Okay, that's too much capacity. So I keep moving down along here. Here's 890, and I get to 788, and that's a W12 by 136. So that'll work.
Hey, why are you using the white columns instead of the gray columns?
What doesn't show up in your handout is that in all throughout the code, that A36 steel, back in focus,
I see.
A36 steel, or yield of 36, is unshaded, and the tabular values for 50 KSI steel is shaded. Okay, watch out. Make sure you're in the right table.
So you just pull the table right out of the, pull the design right out of the table.
Yeah. Okay, let me go another 10 minutes, and then we'll take a short break. I want to get into beams, because typically you see that on this exam. For steel beams, the failure or limit states that you have to design to are for flexure, bending. Typically that may involve lateral torsional buckling, which we'll talk about in a second. Usually you design for flexure, and then you go back and check for shear, deflection, and bearing. Bearing meaning check for the effect of concentrated loads. Okay, looking in at a steel beam, you know, we have one that's simply supported in the next view. Again, this is going to bend. Typically what we do, we orientate the beam such that it bends about its strong axis, or for a W shape, it's the XX axis, because that gives us the highest moment of inertia, and the moment of inertia relates to our bending strength. Sometimes you may have beams bent about the weak axis, like shown here, but that doesn't happen too often. Okay, new to LRFD as opposed to ASD is that now the moment capacity is based on what we call the plastic moment capacity. Okay, instead of using the section modulus, elastic section modulus, maybe you saw this in an earlier session, S, which is I over C. Okay, typically we don't use that now in LRFD. Instead, we use what's called the plastic section modulus, or Z. And Z sub x meaning it's the section modulus about the x-axis. Now what we do is we take that, multiply it by Fy times 0.9, and what that does is it gives us the maximum moment capacity of the beam. Okay, what the plastic section modulus does is it gives